Hello everyone, welcome to another video in the graphs and networks tutorial. In this video I'll be discussing about degree sequence, what it is, and a couple of questions related to that. Alright, so a sequence of non-negative integers d1 d2 up to dp, is called a degree sequence of some graph G if degree of ui equal to di for some I where I lies between 1 and p, 1 is inclusive, and d1 d2 d3 up to dp all are greater than equal to 0. So this sequence is said to be a graphical sequence if it is the degree sequence of some graph. So say you've got some graph, you write down its degree sequence, which is basically a sequence formed by writing down the degrees of each vertex. For referring to the degree of each vertex, I've made another video. I'll just put that I tab above so you can go check that out. Now there is also a corollary from the proof in the previous video. I discussed a proof of one of the most fundamental theorems in graph theory, which will be used almost everywhere in every question we encounter. So it's highly recommended that you check out the previous video if you haven't. That will give you more insight on the proof. Alright, I'll attach that I banner. Alright, so the corollary states that the number of odd degree vertices are even in number. So of a degree sequence, any vertex which has odd degree as its degree will always occur even number of times. So there can't be odd number of times where an odd degree occurs. Okay, let's try solving one question. So this was asked in 2017-18 midterm paper in our college. So let's try solving this. Okay, so it says that does there exist a graph with order equal to 7 and size equal to 12 such that the degree of each vertex is either 2, 3 or 4, and you're supposed to write down the degree sequence of the graph as well. Alright, so let's first start by assuming some things. So let x be the number of vertices with degree 2. Similarly, let y be the number of vertices with degree 3, and therefore we have 7 minus x minus y be the number of vertices with degree 4. Alright, because it's given that your order is 7 and size is 12. So for those who don't know, order is equal to your number of vertices and size is number of edges. Alright, so now we'll use the theorem that we proved in the previous video. It states that the sum of all the degrees equals twice the number of edges. Alright, so using that we have 2 times x plus 3 times y plus 4 times 7 minus x minus y equal to 24. Alright, solving this we have 2x plus 3y plus 28 minus 4x minus 4y equal to 24, which in turn results into 2x plus y equal to 4. Now we see that it has been given in your question that there does exist some vertex with degree 2. So that means that x cannot be equal to 0. Similarly for y. Alright, so this is a important point. Now we will try to find integral solutions to this equation. So one particular solution is that x equal to 1 and y equal to 2, which means that we have our answer as, just a moment, we have our answer as one vertex of degree 2, 2 vertices of degree 3, and 7 minus 2 minus 1 equal to 4 vertices of degree 4, right? And for the degree sequence, we just write it as this. So 4 times 4, 2 times 3, and 1 times 2. So that's your degree sequence. Alright, let's discuss another question. So this was asked in 2018-19 in the midterm. Alright, so there are 25 telephones in a town. Is it possible to connect them with wires so that each phone is connected to exactly 7 other telephones? So you can visualize this as a graph. So each vertex in your graph is a telephone, and a wire that connects your telephones is analogous to your edge in your graph. Alright, so it can be thought of as a graph. So in your graph you have 25 vertices, and it has been given that each vertex is connected to 7 other vertices, and exactly connected. Now, so that means that you have got 25 vertices multiplied by 7 degrees. So that means that degree of each vertex is 7, right? Right. So using the same theorem, this is essentially the same as summation of degree of E, right? But since the degree is same for all, we just write it as multiplication. Therefore 25 times 7 is equal to twice the number of edges. Therefore we get the number of edges as 25 multiplied by 7 by 2. So this is 175 by 2. Now this is a decimal, right? You can't have a proper integer as a solution, right? Now we made an assumption that the edges is analogous to the wires, right? And it is pretty obvious that you can't have wires which are decimals, right? You can't have fractional wires, right? It's not possible. This can't happen. So that means that you cannot make any such connection, which means that no such connection exists. All right. So these were some of the questions that you might encounter on the degree sequence. So these were the simplest and basic level questions. There are pretty higher level questions, but to solve these, those you need the use of one theorem known as the Havell-Hakimi theorem, which I will discuss in the next video. All right. So to summarize, in this video we learned about degree sequences, and we solved 2 questions pertaining to the degree sequence. All right. So that's it for this video. Hope you find it helpful. If you found it helpful in any way, please make sure to like, share, and subscribe to my channel. It will mean a lot to me, and keep supporting, guys. I'll see you in the next video. Signing off. Bye.